Oi, what's good, YouTube? Today we're going over a paper that's pretty cool. It's about, do our perceptual systems actually perceive reality truthfully or not? I've made videos on this in the past. This one is pretty cool, very long, ugly title, but we're going to get into it, and we're also going to do a little rundown of one of my older experiments back when I was in college. Here is a little sneak peek of what that looks like. I had a whole thing going. But anyways, if you are into the idea of do we perceive reality truthfully or not, then stick around. Uh, Before we get there, like, subscribe, comment, all the YouTube things. Join the Discord to discuss. Support me on with that YouTube join button down below. It's as low as $1 a month. Also on Patreon is an option as well. If you enjoy my content and watch frequently, please go ahead and do that if you can. Follow on Twitter and LinkedIn and all that stuff. Here is my obligatory disclaimer. Today I'm going to put us at 5 stars, given that I actually have a full-on experiment to show y'all a little bit. But anyways, yeah, let's go ahead and get to it. The question is, do we see the world as it truly is? So we're all familiar with illusions, right? Where our perception is inaccurate, but we usually still assume that these are the exceptions that prove the rule rather than being the actual norm. So we're assuming that our perception does actually reflect the external world faithfully. And we would assume so because you would think that your perceptions would only be useful to the degree to which they're accurate. You would think that accuracy implies usefulness and that it's hard to imagine inaccuracy in any way being useful. Now, the interface theory of perception was a theory proposed, I want to say 2012 or 2015 or something, by this guy, Donald Hoffman, who you may have heard of him before. He's been on lots of podcasts. If you're big into consciousness, that kind of thing, he's probably been on a podcast you listen to. And it proposes that our percepts, our perceptions, may almost always differ radically from the ground truth to the extent that even key dimensions of perception, like space and time, may have little to no basis in external reality. This is the thing physicists have been telling us, some at least have been telling us for a while now, is that it doesn't seem like time, especially, actually works the way we perceive it to work. And it seems like there's fundamental flaws in our perception. This Hoffman guy created an evolutionary simulation that kind of, he thinks anyways, or at least he thought, found the reason for that disconnect between what physicists are telling us and what we're actually perceiving. And what it says is that the things we perceive are actually not truthful. They're actually radically different from the ground truth of reality. So this theory is inspired by just evolutionary considerations. The actual original paper was an evolutionary simulation, pretty simple one. The idea being that perception can only be useful and can only have evolved in the first place if it positively impacts our fitness. I'm not referring to physical, like exercise fitness, I'm referring to evolutionary fitness, as in the likelihood that you pass on your genes, right? Our perceptual system in our eyes and brain and touch sensors and taste buds, whatnot, right? Should be shaped by evolution, is the idea here. And what does that imply? It implies that we should therefore not think of perceptual representations in terms of their correspondence to an objective reality, but rather to their underlying utility functions that relate behavior to fitness. So we should not think of our perceptions as reflecting truthful base reality. We should think of our perceptions as having been shaped to reflect what is useful to us as evolutionary organisms. The idea being that if reality differs in some significant way that is orthogonal to utility, meaning unrelated to utility, evolutionary utility, then those differences would have no impact on our fitness. If there are qualities of reality that have no impact on your actual chance, or qualities or structures to reality that have no impact on your actual ability to pass on your genes evolutionarily, then there is no reason, there is no mechanism by which we could have evolved an actual accurate representation of those aspects of reality. And conversely, if there are in fact parts of objective reality, structures to it, qualities of it, uh, that do have fitness benefits that actually are useful evolutionarily, then we would expect those to be incorporated truthfully into our perception. So here is the main graph, main chart from that actual original proposal of this theory. In this evolutionary simulation, they had these little robots, you call them, little computer program that moved around in a grid and looked for, I guess you could call it food. And basically, this food item, or you can think of it as something else. You can think of it as oxygen as well. You can think of it as any type of dimension of reality, any kind of actual hard physical thing. Or there's a whole reason why you can think of it as like space time, whatever. Let's ignore that for now. Think of it for our purposes as oxygen, right? So this being is going around a 10 by 10 grid on the computer, a little simulation, and it is having to move through the grid and pick up, let's call it oxygen, right? And oxygen levels go from, in this case, it's 0 to 100. So no oxygen at all to complete saturation of the air with oxygen. And what Hoffman proposed was that it is probably true for basically anything that it is useful in moderation. Meaning, for oxygen, for example, too little oxygen, obviously you're going to not be able to breathe and die. But also too much oxygen, you can get oxygen poisoning, right? There's actually a reason why we don't have like we did not involve for 100% oxygen in our air kind of thing. It's also very flammable, all this stuff. Or conversely, just like water, for example, right? Zero water, you're going to die of dehydration. Too much water, you're going to literally drown, right? Just by necessity of there being too much water in your environment. So it seems like at least a key assumption of his study was that every single thing you could possibly measure, every single fundamental uh, piece of your environment that you can interact with as an evolutionary being probably has this quality of there is some moderate level which it is useful in, but too little is not a good thing for your fitness, and too much is also not a good thing for your fitness ability to survive, right? The way you look at this on this graph is the x-axis. We're gonna look at the top one here. The x-axis is the amount of oxygen or water or whatever it is in your environment, and then the y-axis is your evolutionary payoff, the utility you get from interacting with that piece of the real world, according to how helpful it is in helping you survive and propagate your genes, right? And you see this curve right here. It's a normal standard distribution bell curve. In the middle is very high payoff, very useful for us evolutionarily. And then off on the left and off on the right, very low payoff. Too little water, you dehydrate. Too much water, you drown, right? Somewhere in the middle is the ideal amount of water to have. Same for oxygen and anything else you possibly think of, right? And then the question is, how do we perceive this actual phenomenon of the real world dimension being the x-axis and the evolutionary payoff being the y-axis? What does our actual perceptual system end up doing and showing us about either reality or the fitness payoff, right? So if we were going to define what would truthful perception look like, what would a perceptual system in your brain that actually aligns with the truth baseline reality, aka the amount of water or amount of oxygen, whatever. And then what we do is represent it first with colors. So we say, okay, red color means some amount of oxygen, yellow means a different amount, green means a different amount, blue means a different amount. Here you can see two examples of two different ways to lay out the actual perception as to what levels of oxygen or water result in you perceiving the given color, red or yellow, whatever it is, right? And for veridical, meaning truthful perceptions, what we define here is we say, okay, uh, if the perception, the color I'm seeing, actually has some meaningful matchup to the underlying reality, aka the x-axis, that's truthful. So here, if you see the color red, you know you are seeing the smallest amount of water, the smallest category, the smallest grouping of water levels, right? 0 to 25, whatever unit that is of water. And then if you see the color yellow, you know you are seeing a larger amount of water than if you had seen red. Yellow is the range of, let's say, 25 to 50, whatever unit that is, water. Anytime you see the color yellow, you know for a fact you are seeing more water than if you saw the color red, right? Same for green, same for blue. The actual color you're perceiving up on this top graph has a direct correspondence to the x-axis, to how much water you're actually seeing. You know that every time you see the color blue, you are seeing 75 to 100 in water, oxygen, whatever it is, and you know that every time you see the color blue, you are seeing more oxygen, water, whatever, than if you had seen the color red, right? That is the definition of veridical, truthful perception up top here, the top graph. But then what Hoffman posited would actually be the case would be an evolutionary perceptual system, meaning the colors you see do not match up to the x-axis to baseline real ground truth. Rather, the colors you see match up to evolutionary fitness payoff, aka this bell curve, right? So in this example, we see blue for the largest amounts of payoff, which corresponds to the mediocre middle amounts of oxygen, water, whatever. That sweet spot, Goldilocks zone in the middle. And we see green right outside of that, yellow right outside of that, and red corresponding to the lowest fitness payoff, the lowest amount of chance that you'll actually succeed and thrive and reproduce, right? And what you notice here is, let's say I am that little robot moving around in a maze trying to figure out where I should go next of my next few path options. If I see one path is the color blue and the other path is the color red, I have two options, right? I see in front of me either a blue or a red. Now suddenly, that blue does tell me useful information about the fitness payoff, at the actual chance that I will succeed as an organism. Blue is better for my evolutionary reproduction chances, right? And I also know that if I see red, according to this bottom graph, then red is bad for my actual chances of surviving and reproducing, right? But I do not know between the two path options, red or blue, I do not know which one actually has more ground truth amount of water, oxygen, whatever. The reason being because the color red corresponds to both zero water, and let's say this is 0 through 10 or 15 or something, and the red also corresponds to 100 water or oxygen, whatever, the highest possible level of it, right? Or let's say it's 90 to 100, this range of red, right? So now suddenly, the colors that I'm viewing, the actual output of my perceptual system, no longer correspond to the ground truth, the x-axis. They now only correspond to the fitness payoff, the y-axis. And suddenly, I'm looking at red or blue. I don't know if red or blue is more or less oxygen, water, whatever, because it could be that, I mean, the blue is definitely in this range of the middle right here, but there could be on that other red path, it could be a dangerous path payoff wise because it's not enough water or because it's way too much water. But I have no clue because my color red fires show the color red gets shown to me both for very little oxygen, water, whatever, and very lots of oxygen, right? And this is what we call evolutionary interface view, an interface perception system, where it doesn't actually try at all to reflect baseline reality, the x-axis. It only cares about reflecting and showing you fitness payoffs. Now, this perspective was dubbed by Hoffman an interface theory because of its metaphorical connection to other familiar types of technological interfaces. In the analogy, a computer desktop represents the underlying information in the computer in terms of folders, icons, and perhaps a trash bin. But the idea of like the fact that you have a little trash bin icon for your recycling bin on your computer, there isn't actually a physical bin with physical trash there, obviously. It's just an icon, just an interface. These are just useful fictions. The reality of, for example, like where a file is stored on your computer, the way files stored on computers, it could be anywhere on that hard drive. It could be split up into pieces. Like the actual reality of how the computer fundamentally works in terms of the ones and the zeros is very, very different from the not just simple, but fundamentally not reflective of baseline reality interface that you see with your computer desktop and all of its folders and icons and the path in your file explorer, right? When you go through your file explorer and you look through trying to find some file of something, right? The path that you follow to get to that file isn't actually reflective of how fundamentally the way in which that file is stored on your hard drive. The hard drive doesn't actually care to order files in the order that you put it in your Finder window in your file explorer. On the hard drive, that can be split up into pieces, thrown some random places. All it is a pointer. And so what we're saying is that the desktop with its mouse and wallpaper background and folders, icons, trash bin does not in any way reflect the underlying truth of the ones and zeros of how the computer actually fundamentally works. And that's why we call it an interface theory, because your computer desktop, your uh, desktop environment, is just an interface. And this interface theory of perception similarly suggests that human perception is really just all a useful fiction, nothing but a user interface to the actual outside world, which may radically distort or even hide the true structure of external reality. Now, obviously, given how crazy that sounds, it has been criticized a ton for many, many reasons. And there's one reason in specific that this paper today will be going into as to a big criticism where they actually do experiments. And what we're doing with these experiments today is we're saying, first up, we're looking at flexibility, right? So perception, we assume, must be flexible enough to serve multiple largely independent goals. In Hoffman's original paper, he only had it with one single goal, one single fitness payoff function. But we're going to say today, hey, wait a minute. Don't I do a bunch of different possible tasks and goals and objectives in a given day as a human, or even just any species? There's collecting food, there's finding a mate, there's finding shelter, all these things on the line, there's subtasks of those. It seems that Hoffman's idea of just looking at one single fitness payoff function might be kind of silly. And then number two, Hoffman's original simulation was very inflexible and just stagnant and didn't actually incorporate any sense of change or differences over time and in response to shifting goals. So here in this study, we're looking at a different example, first thing, of a type of fitness payoff function. Earlier, we saw the ones where the fitness payoff looked kind of like a normal distribution with a big bump in the center and then very small, low fitness off on the edges. But the authors of this paper, just as a first point, wanted to question this idea and say, why is it that we could not have a fitness payoff function in which we actually have monotonically decreasing or increasing, meaning no bump in the middle with edges on the side, but actually just a continuous upwards curve or continuous downwards curve? Why can't we have those out in nature, right? And these are what that would look like. This curve we have going on here. And under this curve, it's pretty funny if you look at this bottom chart right here. Under this monotonically decreasing curve, if we actually have our fitness payoff looks like this, if there is some fundamental real world ground truth dimension along which a lower amount, a zero, whatever that unit is very useful, and a higher amount, a 100 of that unit, is very bad for evolutionary payoff, then what you would actually find is your perceptual system would in fact be veridical, truthful. It would line up with the actual underlying dimension, the x-axis per se, right? Just like how earlier we saw the example of vertical perception, all we need is to have strictly ordered colors here in our setup of every time you see a red, you know for a fact it is less than the yellow. Every time you see a yellow, you know for a fact it's less than the green, etc. Turns out if we actually use this kind of fitness payoff function with this monotonically decreasing curve, we do end up with that. Every single blue is actually less than every single green, etc. It is actually veridical, representative, truthfully, of the x-axis. And that's just one example of a potentially different utility function. Now, personally, I do kind of support the idea of the Gaussian utility functions, meaning bump in the middle and tiny pieces, small values for payoff out on the edges. I think that's kind of by definition almost true. But you don't even actually need that fully. Really, all you need to do their experiment is just different utility functions, slightly different shapes for the actual functions themselves. And these authors suspect that as we allow more and more independent and potentially conflicting goals, and by goals we mean the fitness payoff functions, into the mix, the distinction between an interface and veridical systems will simply collapse, since in the end, the perceptual system that is most fit and most flexible in the context of many shifting goals will be a truthful one. So if you are a being that has not just one goal, but many different goals, you will necessarily have to have experienced, have to have built up a actual truthful perceptual system in order to accommodate all those shifting goals, because you cannot specialize your perceptual system to just one of those goals. And so for their experiment, they use the exact same evolutionary simulation that Hoffman originally used, but all they do is add on a larger number of tasks to actually fulfill at one given time. And here is the actual graph we see where we look at the number of utility functions and the actual, so x-axis, sorry, is the number of generations throughout the simulation, right? The evolutionary simulation of just like these little robot beings having kids and everything and evolving and mutating. And then the y-axis is the percent of simulations where the result is veridical, where the actual pattern of the colors that the robot has learned to see given a given point on the x-axis ends up being veridical truthful. What they find is the number of utility functions, if they do just one utility function, aka they do the exact same thing as Hoffman's original experiments, then they do in fact find there's very, very few of the bots generate truthful perception. But as the number of utility functions that a bot has to actually account for and meet increases, you find that they are encouraged to develop perceptual systems that are more and more truthful according to the underlying x-axis truthful dimension of experience. And the big thing with this study is that these results effectively save the day for perceptual realism, the idea that we do perceive reality truthfully, which is kind of funny, or let's say impressive. Reason being that these simulations, actually, kind of by definition, were designed to stack the deck against the idea of truthful strategies, truthful perception, in at least four ways. First is because all monotonic payoff functions were excluded. What that means is we proposed earlier that idea of a strictly decreasing perceptual system like this one. We proposed this idea earlier. These were not actually used in simulations. In the simulations, we never actually used anything like this. In simulations, we actually did end up using the Gaussian functions, meaning we specifically avoided using fitness payoff functions in a simulation that had a bias towards truthful perception, and we specifically only used ones that were biased towards not truthful perception, if that makes sense. And despite that fact, we still ended up with truthful perceptions as we increased the number of total utility functions. And then the next big reason is because the actual space of possible not truthful perceptual systems is much larger than the space of possible truthful systems. You can do a combinatorics thing where you figure out how many fit our definition of all of the color red is below the color blue, etc., right? And there's actually just way more possible combinations that are not truthful than there are that are truthful. And when you randomly start a population, the first population, by definition, because of that, that randomly started population, the random initializations, will have started off with predominantly not truthful perceptual systems when they just are randomly initialized. And finally, by that same reasoning, any given mutation over the course of the evolution simulation was overwhelmingly biased by an order of magnitude, even more likely to result in a not truthful strategy than do a truthful one. So these we still found a result of truthful perceptions, despite the fact that these beings started off with predominantly not truthful perceptions, and that every single chance they had to change their perceptions was also biased towards becoming less truthful. And despite that fact, the evolutionary pressure of having more than one payoff function to meet at the same time did lead them over time to be forced into truthful perceptions, even though we were biased against those. Now, asterisks on the study and everything, the simulations were quite simple, given that we're only using one single perceptual dimension. This is the same issue with Hoffman's original thing. He was also only using, or he was further only using one single payoff function, whereas they just added more payoff functions here. It'd be interesting to question how the results might change if we do more perceptual dimensions. What happens if we actually create payoff functions that are multi-dimensional payoff functions? And it's curious to think about what would actually happen with this. I actually had this idea a couple years ago, and I've never got around to actually doing it, so very pissed about that. I wonder if there's a new paper since that actually has done. I'm not sure. And then before we sign off, I thought I would show you the experiment I ran a couple years ago. I want to say junior year of college now, where I did my own version of kind of not disproving, but still kind of working within Hoffman's original experiment. So as you can see here, I still had a little bot moving around in a grid, picking up resources, right? Here, the bot's path is the same on the left and the right. The yellow squares, I believe, are higher resource amounts, and the dark deep blue squares are lower resource amounts. And this was just the best bot of some epoch in some generation throughout simulations. I did so many of these. Actually melted an entire M1 MacBook Air back when those first came out. But basically, what I did was I separated out into sensation versus perception. My hypothesis was that we should not be thinking of our perceptions just as a single system, that we should be thinking of it as like our sensation system, aka the set of neurons closest to our actual eyeballs, taste bud receptors, touch receptors, etc., would fundamentally work differently from the ones actually in deep in our brain, our perceptual system, right? The idea being that everything deeper in your brain probably evolves faster and can change faster and adapt to goals faster and adjust itself faster over the course of evolution. Whereas those neurons right actually at your eyeballs and right actually at your touch receptors in your hands and things are probably pretty rigid. They probably change much more slowly. And so what I did was I split them into two things where first off you had a system where the ground truth is still the x-axis. It goes from 0 to 10 in my experiments. And the sensation system has to label that x-axis with I did still colors here. And then the perception system takes your sensory signals as input and gives you a final output, right? And I also posited that because the sensation system is so much more ingrained. I wasn't sure about this part. This is like a weird assumption, but I gave the sensation system more possible colors, more possible outputs to actually use. I assumed it was of higher detail, along with also assuming that it mutated much more slowly. This is a different graph, actually. Yeah, there's so many of these. And what I did for the payoff functions, as you can see here, is I allowed them to alternate, to change over time. They are all still, so every single epoch or so, every single, I think, 1,000 generations of the simulation, the fitness function would actually change. This was to simulate the idea that, oh, over the course of evolution, when you go from rat to eventually chimpanzee to Homo erectus to Homo sapiens, etc. The idea was that fitness functions probably change over time, right? And I had them changing over time. They were still Gaussian in the sense that this leftmost piece and this rightmost piece were always equal to 0, but then the center was allowed to change to whatever it liked. I believe I just set random values, maybe designed ahead of time some specifically made shapes. I think it was random values actually. Yeah. And then what I did was I said, okay, my hypothesis was that the perceptual system up top would actually still function just like Hoffman's original proposal, which was that one color would be used for high fitness payoffs and one color for low fitness payoffs. I did two colors here for my perceptual system in this experiment. That's what Hoffman did originally too. The idea being that one color gets used for low fitness, one color for high fitness. So it is still sticking with his idea of non-veridicality. These reds and blues up top are also non-veridical because if you see the color blue, you don't know if it is more or less of the actual real world x-axis in the color red. Meanwhile, I said, I bet because of this much slower mutating lower level sensory system and having to use it as inputs, I bet that the sensory system will actually stay veridical, meaning there will be none of these gaps, discontinuities of one color to the other. And you can see here that with the exception of the furthermost to the right and furthermost to the left pieces, that actually is true, is that as you move throughout the x-axis, you do not see a repeated color here. It is all new colors. You even see, but the reason that the 0 and the 10, the furthest left, furthest right numbers, are both the same color is because remember the function is Gaussian, aka those two values are always 0. Those two values are always low fitness. So my proposal here was that within the range of for the given real world dimension, within the range of stimuli that are actually used throughout evolutionary epochs, throughout the long term of like many species evolution, in that range, your sensory system is veridical and your perceptual system is not, is interface. But then there is a certain degree of outside that range. Those areas of the actual domain never get used. So if you think about like the visible light spectrum, right? Some animals see colors that we don't. They see slightly more into the ultraviolet or whatever it's called, or infrared, and slightly more into the other end, right? But I don't think any animals see gamma rays, as far as I know, right? There's a certain range of the light spectrum that probably has never been useful to any animals whatsoever, any life, and that range is in fact even our sensory system not veridical, but then the range that does get used and gets used frequently enough among different progressive species over time probably is veridical at our sensory level. And then again, our perceptual system is still non-veridical. I would honestly love to go back and redo this with the idea of multiple payoff functions at the same time and all this stuff. I have so many ideas for this, but it's not my thing anymore. I left psychology for a reason. This stuff is pretty cool though. And this is an AI channel, as you know, so think a little bit about like what does it actually mean? Do we expect AI systems to be viewing the world truthfully, veridically, given their utility functions, given their incentive structures, right? And I would really be curious to think about what y'all's thoughts are on how this might apply to like next token prediction trained models and all this stuff, right? As far as like, to what degree will grounding them in multimodal data actually help them get vertical perceptions versus not, all this stuff. I have yet to really think through anything like that. I haven't touched this topic in so long, but it's something I am still a bit curious about and maybe looking into the future. But other than that, that's the video. Hope y'all enjoyed. Like, subscribe, comment, all the YouTube things. Support me on by hitting that YouTube join button down below, as low as $1 a month, as high as $10 a month if you're a frequent viewer. You can also do so through Patreon. If you want to discuss this stuff with other tuna dorks, join the Discord. Follow me on LinkedIn, Twitter, all that stuff. And yeah, end of the video.